All right, so where we left off, Chemistry 3101, was talking about acid catalyzed hydration. So now what we're going to do is we're going to take our alkene and we're going to add water to it. But the way we're going to think of water is, yes, we can think of it as H2O, but it's easier for us to think about it as a hydrogen and a hydroxyl group, right? Because we're adding a hydrogen to the carbon that's going to get richer in hydrogens, and we're adding to the hydroxyl to the more substituted carbon, and you see that happening right here. Now, normally we write H3O plus as our catalytic amount of acid, or our acid catalyst that we use to add the water across the double bond. But you can also write plus water, and then you can write sulfuric acid in these square brackets. The square brackets refer to the acid as a catalyst. Okay, so what happens when you combine sulfuric acid and water? So if you take H2SO4 and you put it in water, well, there's an equilibrium between hydronium and the hydrogen sulfate ion, and the equilibrium is going to lie to the side of the hydronium. Why? Because this has a pKa that's equal to -2, and sulfuric acid has a pKa that's equal to -9. So that means that when we combine water and sulfuric acid, what do we have mostly? We have mostly hydronium ion. So if you're wondering about evidence for this mechanism, how do we know that it proceeds through a carbocation intermediate? The reason why is if you look at the reaction rates, whether you form a primary carbocation versus a secondary versus a tertiary, as you go from primary to secondary to tertiary, you see the rate increases by from 1 to 10 to the power of 11, okay? So that's one of the evidences that we proceed through a carbocation intermediate in our mechanism. Now, the mechanism, this is one that you have to know, okay? The first step is just a proton transfer, right? So we take our acid catalyst, which is our hydronium molecule here. We add our proton. Remember, the rich get what? Get richer. It's a Markovnikov addition. We form the most stable carbocation. In this case, it happens to be a tertiary carbocation. And then our nucleophile comes in, but instead of getting our final product, we're going to end up with what? We're going to end up with what's called an oxonium ion, right? Because we're going to have a positive charge on our oxygen, and we call this an oxonium ion. So what do we have to do next? Is that the oxonium ion is going to be deprotonated by water. And then when the water picks up a proton, you not only get the product, you get the product, plus you also regenerate the acid catalyst, right? It reforms, and so it's ready to react again. So again, not only do you have to know the mechanism for the hydrohalogenation across a double bond of an alkene, but you also have to know the mechanism for Markovnikov addition of water across a double bond. Well, with all that in mind, you should be able to put this together that if we use dilute sulfuric acid, right? So this is just an acid catalyst, right? This is H3O plus, okay? We end up with addition, right? This is addition of water across our double bond. However, if we heat it up with sulfuric acid, so concentrated sulfuric acid, then we get elimination. So elimination, and I'll just put elimination like that. Okay, so depending on whether we use dilute, we get addition. If we use concentrated, we get elimination. And so if we're synthesizing an alcohol, we would use excess water, whereas if we're synthesizing an alkene, we're going to use excess acid and very, very little water. So it's based off Le Chatelier's principle, right? If you have a lot of this, it's going to push the reaction in this direction. But if you put it in sulfuric acid, you have like no water. So then it's going to push it towards the formation of the water. There we go. Now, again, if you proceed through a carbocation intermediate, so in the first step, we're going to take our hydronium molecule or ion, and we're going to do our proton transfer. So the rich are going to get richer. So we're going to get something that looks like this. Let's draw the carbocation that results. So in this case, it's going to look like this. Am I missing a carbon? 1, 2, 3, 4. Yeah, I knew I was. There we go. We're going to end up with this carbocation. But remember, the nucleophile, the water, can attack from either face of the molecule because the carbocation is trigonal planar. And so in this particular case, we are going to end up with a racemic mixture. So you need to be aware of that, okay? You need to be completely aware of situations where you're going to end up with a racemic mixture. So with all that in mind, let's see if we can solve this problem, which asks us to draw a mechanism for this transformation. And so could anybody tell me what the first step is going to be? Is it going to be a proton transfer, a nucleophilic attack, a loss of leaving group, or a rearrangement when I treat this alkene with hydronium? And it's not a trick. Could anybody tell me what the first step of the mechanism is going to be? Based on, exactly. Thanks, Lauren. It's a proton transfer. Now, if I highlight this carbon in red and this carbon in blue, could anybody tell me where is the proton going? Should it go to the carbon in red or to the carbon in blue? Remember, it's going to be a Markov-Nikov addition. Which carbon is richer in hydrogens? Is it the red one or the blue one? It's going to go to the red one, right? Because the red one has 2 hydrogens, whereas the blue one only has 1 hydrogen. So the rich are going to get richer. Exactly. So it's going to go where the red carbon is. So I can drag my curved arrow through that, pick up the proton, excuse me, and I'm going to end up with this carbocation. You can clearly see that the nucleophile, your water, does not attack, excuse me, at that carbon. Why is that? Can anybody tell me why? What's going to happen next? So this was our proton transfer. What would be the next mechanistic step? Would it be a proton transfer, loss of leaving group? There you go. Thanks, Hannah. It's going to be a carbocation rearrangement, isn't it? It's going to be a rearrangement because this hydride is going to shift, that arrow, it's going to shift like this so that we go from a secondary carbocation to a tertiary carbocation, right? We go from secondary to tertiary. And so now the next step is going to be my nucleophilic attack, where my water can come in and attack like that. And we're going to produce our oxonium ion. Where's my black pen? Just going to look like this. So we end up with our oxonium. And then the next step is going to be a proton transfer, where water is going to come in as a base. I'll just shorten my water like that. And there you go. And you're going to form your alcohol like that. So proton transfer followed by a rearrangement followed by 2 more proton transfers, and we end up with our alcohol. Now, what if you have this reaction and you don't want a carbocation rearrangement to occur? So then the question would be, can we avoid the carbocation rearrangement? Okay, is that possible? The answer is yes, we can. The way we do it is by doing something called oxymercuration demercuration. So if we took that same old alkene, this guy here, and we do this 2-step process. The first step is that we treat it with what's called mercuric acetate or mercury 2 acetate, which is this, in water. And then in the second step, we treat it with sodium borohydride. Okay? In that case, we're going to get a Markov-Nikov addition, but we're going to get no rearrangements. And this is called oxymercuration demercuration. And that is going to be the topic of the next section. So, oxymercuration demercuration overview. So it says here that Markov-Nikov hydration, which is where we combine water and sulfuric acid, but when we combine those two, what do they make? They make H3O plus, has a limited application. Why? Because we see that rearrangements can occur, right? It gives you a mixture because of rearrangements. So how do we avoid that? We use oxymercuration demercuration, which is a 2-step process. What's the overview? Is that number 1, it gives you Markov-Nikov addition and no rearrangements occur. So again, it gives you Markov-Nikov addition, but there's no rearrangements that occur. Now, what's interesting here is that you see we use mercury. So I'll tell you right now, the only time I, as a chemist, want to get mercury out in a lab is when I have no alternative, okay? I don't like to use mercury. It's a nasty element to work with. It's difficult to dispose of, but sometimes you just have to go for it. So why would this happen with this oxymercuration, demercuration? Well, mercuric acetate, which you can also call, could also be known as mercury 2 acetate. They mean the same thing, okay? And acetate is this. So if I have OAC, it's this, okay? So this is, oh, I guess it's written over here. I didn't even notice. But the OAC minus is this. So this is O minus AC. Okay, so it's an acetyl group with an oxygen attached to it, so we call it an acetate ion. So anyhow, we have mercury 2 acetate or mercuric acetate, which spontaneously breaks apart to give you, or is in equilibrium with this mercuric cation. Now you can imagine that this mercuric cation is a good, electrophile. I mean, it's got a positive charge right on it, and it is a good electrophile. And so what's going to happen is, instead of getting a proton transfer to form the most stable carbocation, what's going to happen is the mercurinium ion is going to, this mercuric cation, which we call the mercurinium ion. Anyhow, I noticed that it wasn't written on that slide. But anyhow, the mercurinium ion is going to be formed when the mercuric cation reacts with the double bond. So let me rephrase that, okay? So this is the mercuric cation. Again, choose my words carefully. Mercuric cation, which is this, which is in equilibrium with the mercuric acetate. The mercuric cation gets attacked by the double bond to make the mercurinium ion, okay? And if you look at the mercurinium ion here, you see these two resonance forms here where you have this three-membered ring here. Well, you notice that in the other one, okay, this one here, that you have the tertiary carbocation. And so that explains why the water comes in and it attacks at the most substituted carbon. So what's going to happen here is that your nucleophile, which is going to be H2O, okay, and it's going to come in and it's going to attack at the most substituted carbon. Why? Because that's the one that's better at stabilizing this partial positive charge, okay? So then, to get rid of all of this and to convert it into a hydrogen, you use sodium borohydride. There is no mechanism provided in the textbook for that, for the demercuration step whatsoever, because it's thought that it proceeds via a free radical mechanism. And we don't really talk about radicals until we get to chapter 10, okay? So there's not even a little bit of a mechanism for that. Now, as far as this mechanism goes, this thing here, I'm going to even write it here in my slides for you, okay? Will not ask. Okay, I'm not going to ask you, I'll just put will not ask to draw, okay, that mechanism. But I expect you to understand the rationale. I expect you to understand that once you form the mercurinium ion, okay, that the nucleophile is going to attack at the most substituted carbon. Why? Because it's best at stabilizing the partial positive charge. So that's why we get Markov-Nikov addition, but there's no rearrangement whatsoever. And so here's the bottom line. If you have some kind of alkene like this, which you can form a carbocation, if I drew the carbocation, it's going to look, son of a gun, it's going to look like this. You know that that's going to undergo a rearrangement to give you this carbocation. In that case, you end up with this product and you end up with this product, right? So you end up with both products in that particular case. But if you do oxymercuration, demercuration, which is the first step, is mercury 2 acetate or mercuric acetate in water, followed by, it's a complete different step. Second step is sodium borohydride. That gives you Markov-Nikov addition, but again, there's no rearrangement. Okay, so no rearrangement and Markov-Nikov addition. So if you're wondering, and I very rarely have students ask me this, but every once in a while somebody will say, well, does that mean I can just use this for every Markov-Nikov addition? No. The only time you should use these conditions are when you're trying to avoid a rearrangement. I'll tell you why. It's because why else would you get mercury out? Okay, mercury, like I said, is very difficult to dispose of and it's toxic. So that's the only time we use oxymercuration, demercuration. So as far as question 8.16 goes, I'm just going to solve the first one with you. And I want you to take a look at 8.16b on your own. Now it says predict the product for each reaction and predict the products if the acid catalyzed hydration had been performed other than oxymercuration, demercuration. So if we do an oxymercuration, demercuration, it's going to be Markov-Nakov addition of water across that double bond. If I highlight this carbon in blue and this carbon in red, could anybody tell me which one of those carbons is going to take the hydroxyl group? Will it be the blue carbon or the red carbon? Keep in mind, it's Markov-Nakov addition. It's going to be the blue. Thanks, Lauren. And there's going to be no rearrangement. So the product, like Lauren said, is just going to be this. Okay, we're going to end up with this compound here. Now, it doesn't tell us anything about stereochemistry, but we're going to end up with a racemic mixture. In this case, we get a stereo center right here, but I'm not really concerned with that. Okay, I'm not going to ask you about that. Now, if I was to do an acid catalyzed hydration, what's going to happen in that case? What's going to happen is this, is you're going to do the Markov-Nakov addition of the hydronium to that double bond. Just bear with me here. This isn't my best artistry, but anyhow, you're going to do a Markov-Nakov addition like this, but that's going to give you a secondary carbocation, right? You're going to end up with a secondary carbocation, and that secondary carbocation is going to undergo a methide shift like this, and then you're going to end up with also a tertiary carbocation like this. So you're going to end up with both of these, and then after you do the nucleophilic attack followed by the proton transfer, so that's why I'm putting two arrows because I'm not drawing the whole mechanism out, you're going to end up with this compound, which is the product from no rearrangement. Okay, so no rearrangement, and then you're also going to end up with the product from the rearrangement, which is going to be, can make that a little prettier, which is going to be this product like that. So you're going to end up with a mixture of two different products in this specific case. So if you want to avoid that carbocation rearrangement, you've got to use oxymercuration, demercuration. So give me a thumbs up if you're with me on the rationale or the idea of why you would use oxymercuration, demercuration. Again, avoid carbocation rearrangement. That's exactly why we use oxymercuration and demercuration. Well, so far, all we've talked about is Markov-Nakov addition of water across a double bond. Right? Remember we talked about Markov-Nakov addition of HBr and then anti-Markov-Nakov addition of HBr? If you're wondering, can I do an anti-Markov-Nakov addition of water? The answer is yes. This is anti-Markov-Nakov addition of H2O. So now it's not the rich getting richer. It's the rich taking the hydroxyl and the other carbon taking the proton. And the answer to that is using something called hydroboration oxidation. And the mechanism is provided in our textbook. I'll show you right here. You just scroll down. It's shown all the way down here. I'm going to put here, will not ask mechanism. It doesn't mean it's not important to look at it, because it does provide you with a rationale as to why anti-Markov-Nakov addition occurs. And you can see that the textbook goes into all kinds of information about it. But the bottom line is it's a two-step process, okay? The first step is using borane and THF. Now, let me unpack some of this. So BH3, this is called borane, okay? THF stands for tetrahydrofuran, and THF is this compound. It's a cyclic ether like that. And then in the second step, you use hydrogen peroxide and sodium hydroxide. And the bottom line is that you get anti-Markov-Nakov addition of water across your double bond. So this carbon is richer in hydrogens, and so it's the one that takes the hydroxyl. The other carbon that is poorer in hydrogens, it takes the hydrogen. So the thing about the hydroboration oxidation is not only is it regioselective for anti-Markovnikov, it's also stereoselective. What happens is that the hydrogen and the hydroxyl group are added in a syn fashion. In syn fashion means same face of pi bond when they're added. So take a look at this compound here. Here's your pi bond. It's going to be anti-Markovnikov addition. And so the hydroxyl and the proton are going to be added on the same face. So see here, they're both wedges, or you could draw them as both dashes. Now, what's the relationship between these two compounds is that they're enantiomers. However, if you're wondering, could one be a wedge and one be a dash? The answer is no. That's called anti-addition, and that does not happen. This is actually tested on the ACS final. Okay, ACS loves to test on this. So they love to ask questions about hydroboration oxidation and make sure that students understand not only is it anti-Markovnikov, but it's also a syn addition. So a little bit about this whole borane THF thing. If you're wondering, it says BH3 dot THF. What is this dot that's just floating in midair? Let me explain that to you, okay? So you know that the hybridization of the boron in borane, BH3, is sp2. It has an empty p orbital, and so that means it's going to act as a Lewis acid or an electron acceptor. And so when we have borane, BH3, it can accept a pair of electrons. Now, something that borane will do sometimes is, since the boron doesn't have an octet, it'll form a dimer with another borane molecule to form this kind of B2H6 thing here, which is like the dimer, and it has two electrons spread over 3 atoms like this. We used to call these banana bonds when I was a student. They don't call them that anymore. But anyhow, the whole idea of the 3-center 2-electron bond is formed in B2H6. I'll tell you right now, the ACS and the MCAT, I don't remember if the DAT does it, but I know they like to use B2H6 instead of borane sometimes. But in our textbook, he'll always use BH3THF. Okay, he'll always write that out. And if you're wondering, well, what's the THF for? It's because your THF, this acts as a Lewis acid, and this acts as a Lewis base, and it donates a pair of electrons. And so when you form this Zwitter ion here, okay, we just write that as BH3 dot THF. Okay, it's like a complex between the boron and the oxygen. And again, instead of writing that out, sometimes the ACS likes to write B2H6. Okay, and I think the MCAT does that too. Either one is totally acceptable. But again, our textbook, Klein, Dr. David Klein, who's the author of our textbook, he likes to write it that way. All right, so there you go. So why do we get anti-Markovnikov regioselectivity? Well, there's quite a bit of information given in here, and you don't really need to know all the ifs, ands, or all the rationale behind it, but I'll just kind of run over it with you quickly. Is what happens is when the borane, right, this is your BH3, this is your borane, and this is your unsymmetrical alkene, when they add together, is that you end up with the hydrogen being added to the less substituted carbon, and the BH2 group adds to the more substituted carbon. I think that's the easiest way to remember it. And then the boron just gets replaced with the hydroxyl group in the end. But, and you can totally think of it as being that way. But what happens is after the first addition, it keeps adding over and over and over until you end up with a trialkyl borane. And then the trialkyl borane reacts with hydrogen peroxide. So I think the easiest way to remember it is in terms of sterics. So again, the hydrogen goes to the more substituted carbon, and the boron, which is bigger, goes to the more substituted carbon. Again, I think by far the easiest way to do it is just think of sterics, okay? However, there is an electronic component, but I'm not going to worry about that right now. So the whole mechanism is uncovered here. You form the trialkyl borane, and then, like I said, the hydrogen peroxide reacts with hydroxide. You end up with this anion, which reacts with the trialkyl borane. then it undergoes a rearrangement until you make a trialkoxyborane, and then you get a nucleophilic attack, and then a loss of leaving group, and then a proton transfer in the end. Again, I'm not going to ask you this. I think the most important part of this entire mechanism really is just this first step, that you understand that the hydrogen goes to the more substituted carbon, the boron goes to the less substituted carbon, and eventually the boron, where is it here, gets replaced by a hydroxyl group. That's really the main thing that you have to know. Okay, so again, hydroboration oxidation is stereospecific. We only get syn addition. If you form only one chiral center, however, though, then in that case you end up with just a pair of enantiomers, and you'll end up with a racemic mixture. So if you end up with two chiral centers, in that case, you're going to end up with a pair of enantiomers, 50-50. There's going to be no differentiation between either one. So with that in mind, let's see if we can predict the products of this reaction here. So we have an unsymmetrical alkene. We're going to do a hydroboration oxidation. So remember, this is going to be it's going to be anti-Markovnikov addition. So if I label this carbon in red and I'll put this one in blue, could anybody tell me which one of those carbons is going to take the hydroxyl? If it's going to be anti-Markovnikov, which one will take the hydroxyl? Will it be red or blue? Remember, it's anti-Markovnikov, right? So it's the red one, right? The red one is richer in hydrogen. So now if it's anti, it's going to take the hydroxyl. That's right. And is this going to be syn addition or anti addition? Does anybody remember? And it's not a trick. We just went over it. Hydroboration oxidation. Is it syn addition or anti addition? Do the hydroxyl and the proton get added to the same face of the molecule or opposite faces of the molecule? Exactly. It's syn addition. So syn addition. So that means, again, the hydroxyl and the proton are going to be added to the same face of the molecule. So let's draw our 5-membered ring. It's going to look something like that. We didn't touch this methyl group whatsoever, so we'll leave that there. So we're going to have the hydroxyl. I'll put it on a dash like this, which means that the proton is also going to be on a dash like that, which would mean that this methyl group is going to be on a wedge like that. Now, there's no need for me to put that proton in. I can just leave it out and just leave the methyl group as a wedge, because that implies that the proton is going to be going down, that it's syn addition. So not only am I going to get this product, but I'm also going to get, so let me just copy and paste this. So copy and paste this one over here. And then I'll have a question for you. But I'm also going to end up with a situation where the hydroxyl group is going to be pointing up, and the proton here is going to be pointing up. Therefore, the methyl group is going to be pointing down like that. Could anybody tell me the relationship between those two compounds? Go back to think of your chapter 5. What would the relationship between those compounds be? Would anybody tell me the relationship? Are they enantiomers? Exactly. Thanks, Jenny. Right? One of the stereocenters didn't change, but the other ones did. So these are not enantiomers. These are diastereomers. There you go. Awesome. There we go. So you see that the answer is here on the next slide. I don't know why I put it in there. The reason we don't get a pair of enantiomers is because it already had a chiral center. Already had a chiral center, and that chiral center wasn't part of the site of the reaction at all. So with that in mind, let's see if we can solve a couple of anti-Markovnikov addition problems here. So we're doing anti-Markovnikovs. Remember, since it's hydroboration oxidation, so it's going to be anti-Mark, and it's going to be syn addition. All right. So with the first one, if it's going to be anti-Markovnikov, We have two carbons. The carbon in red is richer in hydrogens, so that's the one that's going to take the hydroxyl. I'll draw it as a wedge like that. That means that the proton would also be a wedge. We don't need to put that in there though, because that's not a chiral center. So I can just leave that out. But remember, I'm also going to get the opposite, where the hydroxyl is a dash and the proton is a dash. So I'm going to get this plus it's an enantiomer. So I'm going to get this. So these two compounds, what's their relationship? Is these are enantiomers. Enantiomers. And then for the next one, am I going to have a chiral center formed in the next one? If I highlight this carbon in red and this carbon in green, kind of a Christmas themed molecule here, which one of those carbons is going to take the hydroxyl? Would it be the carbon in red or the carbon in green? So remember, this is anti-Markovnikov, right? So the one that is richer in hydrogens now is going to take, right? So it's going to be opposite. So the red one is richer in hydrogens, so it's not going to take the hydrogen. It's going to take the hydroxyl. So we're going to end up with this compound. So we're going to end up with a primary alcohol. All right, and there's no chiral centers. So no chiral centers. There you go. All right, now if you took this molecule and you did a Markovnikov addition, right, with H3O plus, in that case, you would end up with this compound. So you see how that we can control the regioselectivity, whether we use Markovnikov or anti-Markovnikov. So this would be Markovnikov addition. But again, hydroboration oxidation is anti-Markovnikov and is a syn addition.